Hello everyone. Today we are going to analyze this beam using moment distribution method. Before analyzing, let us see the beam one time. In this beam, we are having two spans, span AB and span BC. In the span AB, we are having a point load acting on the center. In the span BC, we are having uniformly distributed load acting for the full span. Span AB is 10 meter long, span BC is 8 meter long. There are three supports in this beam, in the point A, in the point B, and in the point C. There are supports. All the supports are roller supports. In the point A and in the point C, we are having roller supported ends. In the roller supported end, there will be no movement, only there will be the vertical reactions. So in the point A, MAB will be 0 and in the point C, MCB will be 0. In the joints, there will be two movements. In the joint B, we are having two movements. One movement will be acting in the clockwise direction and another will be in the anti-clockwise direction. But both of the moments will be having the same value. So in this analysis, we have to find two moments and three reactions RA, RB and RC. Now let us make the fixed end moments. For making the fixed end moments, we have to assume every span as a separate fixed beam. First, let us make the fixed end moments in the span AB. You can see that I have assumed the span AB as a separate fixed beam. In this table, you can see some of the important fixed end moments for the different type of loadings. In the span AB, we are having point load acting on the center, so we have to select this condition. The formula for the fixed end moments are minus WL upon 8 and positive WL upon 8. In the span BC, we are having UDL acting for the full span. So we have to select this condition. The formula for the fixed end moments are minus WL square upon 12 and positive WL square upon 12. In the span AB, we are having a point load acting on the center. We just saw the fixed end moment formulas minus WL upon 8 and positive WL upon 8. M of AB is negative because it is acting in the anticlockwise direction. M of BA is positive because it is acting in the clockwise direction. Let us apply the values in the formula. W is 72, L is 10. After applying, we are getting M of AB is equal to minus 90 kN meter and M of BA is equal to 90 kN meter. Now let us make the fixed end moments in the span BC. In the span BC, we are having UDL acting for the full span. We already saw the formula for the fixed end moments. Minus WL square upon 12 and WL square upon 12. Let us apply the values inside the formula. W is 36 and L is 8. After applying, we are getting M of BC is equal to minus 192 kN meter. M of CB is equal to 192 kN meter. In the moment distribution method, we have to calculate the distribution factor. We have to calculate the distribution factor only in the joints because in the ends, we can easily say the distribution factor. In the fixed ends, the distribution factor will be 0. In the hinged and roller supported ends, the distribution factor will be 1. Here we are having the ends A and C. For both of them, we are having roller supported ends. So the distribution factor for AB will be 1 and the distribution factor for CB also will be 1. In this case, we have to calculate the distribution factor only in the joint B. For calculating the distribution factor, we have to find the stiffness. Let's see the formula to calculate the stiffness. If the parent is fixed, the formula is 4EI upon L. If the parent is hinged or with roller support, the formula is 3EI upon L. If the parent is continuous, the formula is 4EI upon L. Using the formula, we can calculate the stiffness and then we have to calculate the distribution factor. Let us calculate them. From the joint B, we have to calculate two stiffness values for BA and for BC. First, let us calculate for BA. For that, from the joint B, we have to look at the point A. In the point A, we are having a roller support. If the parent is having roller support, the formula for stiffness is 3EI upon L. The length of AB is 10 meter, we can apply. Finally, we are getting 0.3 EI. Now, let us calculate the stiffness for BC. For that, from the joint B, we have to look at the point C. In the point C also, we are having a roller support. If the parent is having roller support, the formula is 3EI upon L. The length of BC is 8 meter, we can apply. Finally, we are getting the stiffness is equal to 0.375 EI. We have calculated the stiffness K. Now, let us calculate the summation of stiffness, that is sigma K. To calculate sigma K, we have to add these two stiffness values. After adding, we are getting 0.675 EI. Now, let us calculate the distribution factor. The formula for the distribution factor is K by summation of K. For BA, K is 0.3 EI, sigma K is 0.675 EI. When we apply the formula, we are getting 0.4444. For BC, K is 0.375 EI, summation of K is 0.675 EI. When we apply in the formula, we are getting 0.5556. Now, let's start making the moment distribution table. First, let us enter all of the members. Then, let's enter the distribution factor values. We already know the distribution factor for AB is 1 because in the point A, we are having a roller support. For CB also, the distribution factor is 1 because in the point C also, we are having roller support. For BA and BC, we have already calculated the distribution factors. Let us enter them. Then let us enter the fixed end moments. We know that in the points A and C, the moment will be 0 because they are simply supported ends. So MAB will be 0 and MCB will be 0. In this table, we have to make AB and CB 0. For AB, the fixed end moment is minus 90. When we add 90 with this minus 90, we will get 0. For CB, the fixed end moment is 192. When we add minus 192 with this 192, we will get 0. In this way, we can make AB and CB 0. We have released AB and CB. Now we have to give the carryover from AB to BA and CB to BC. From AB, half of 90 will go to BA. 90 upon 2, we will get 45. From CB, half of minus 192 will go to BC. Minus 192 upon 2, we will get minus 96. Now let's make the adjusted fixed end moments. When we add these two moments, we will get 135. When we add these two moments, we will get minus 288. Now let us make the first distribution. The distribution can be done only in the joint. We are having only one joint, that is joint B. In this joint, we are having BA and BC. For BA and BC, we are having fixed end moments. For making the distribution, we have to add these two fixed end moments. Then we have to multiply with the distribution factor. First, let us make the distribution for BA. For that, we have to add these two values and multiply with the distribution factor for BA. When we do that, we are getting negative value. If we get a negative value, we have to enter inside the table as positive. And if we get a positive value, we have to enter inside the table as negative. Now we have got a negative value. So we are entering inside the table as positive. Now let's make the distribution for BC. For that we have to add these two values and then multiply with the distribution factor at BC. When we do that, we are getting a negative value. So we are entering inside the table as positive. Now we have to make the carryover. We cannot make the carryover between AB and BA because we have already released AB and made it as 0. Also, we cannot make the carryover between BC and CB because we have released CB and made it as 0 already. In this case, we cannot continue further. Let us add the values and find out the final moments. We have to add the values from the adjusted fixed end moments. That is why I have made the color line. Below this color line, we have to add the values. When we add these two values, we are getting 203. When we add these two values, we are getting minus 203. So in this analysis, we have calculated all of the moments. In this beam, we have calculated the final moments. For MBA, we are getting a positive value. That means it is acting in the clockwise direction. For MBC, we are getting a negative value. That means it is acting in the anti-clockwise direction. Now let us calculate the reactions. First, let us take the span AB and calculate the reactions. In the span AB, we are having a moment MBA which is acting in the clockwise direction. So when we calculate the reactions in the span AB, we have to take the moment MBA. In this span, first I am going to calculate the reaction RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. The reaction RA is acting towards the point B in the clockwise direction. So it will be positive and the distance is 10 meter. So 10 RA. The point load is acting towards the point B in the anti-clockwise direction, so it will be negative and the distance is 5 meter. So minus 72 into 5, the moment is acting in the clockwise direction, so it will be positive. Finally, we are getting RA is equal to 15.7 kilonewton. To find out RB1, let us apply the rule summation of vertical forces is equal to 0. We are having three vertical forces, RA and RB1 are acting upwards, so they will be positive. The point load 72 kN is acting downwards, so it will be negative. RA we have already calculated, we can apply that. After calculation, we are getting RB1 is equal to 56.3 kN. Now let us take the span BC and find out the reactions. In the span BC, we are having an anticlockwise movement MBC, which is equal to 203. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. In this case also, I am moving towards right hand side. Clockwise will be positive, anti-clockwise will be negative. RB2 is acting towards the point C in the clockwise direction, so it will be positive, and the distance is 8 meter, so 8 RB2. The UDL is acting towards the point C in the anti-clockwise direction, so it will be negative, and the distance is 8 meter. When the UDL comes, we have to multiply with the distance and the distance by 2, so 8 by 2. The moment is acting in the anti-clockwise direction, so it will be negative. Finally, we are getting RB2 is equal to 169.375 kilonewton. Now let us apply the rule summation of vertical forces is equal to 0. Here we are having three vertical forces, RB2 and RC are acting upwards, so they will be positive. The UDL is acting downwards, so it will be negative. When the UDL comes, we have to multiply with the distance to get the total load. Finally, we are getting RC. We have calculated the reaction in the point B 2 times. So let us add them. Finally, we are getting RB. Now we are going to draw the shear force diagram. Before drawing shear force diagram, let us calculate the shear force values. I am calculating the shear force values from the point A to the point C. In this case, I am moving towards right hand side. The upward forces will be positive. The downward forces will be negative. You can see the calculations here. For the point loads, we have to calculate the shear force at just left of the point and just right of the point. Now you can see the shear force diagram. If there is UDL, the shear force line will be inclined. You can see that in the span BC we are having UDL, that is why we are getting inclined line. For the point loads, it will be a straight line. In the shear force diagram, if you are getting negative values, we have to draw below this line. If you are getting positive values, we have to draw above the line and then mark positive and negative. Now let us make the bending moment diagram. For that, first we have to make the free moment diagram, then end moment diagram. After, we have to combine both of them to get the bending moment diagram. For making the free moment diagram, we have to consider each span as a separate simply supported beam and then draw the bending moment diagrams. In a simply supported beam, if the point load is acting on the center, the formula for maximum bending moment on the center is WL upon 4. Here W is 72, L is 10. We can apply in the formula, finally getting 180 kilonewton meter. In the simply supported beam, if the UDL is acting for the full span, the formula for bending moment is WL square upon 8. Here W is 36, L is 8. We can apply in the formula, finally getting 288 kilonewton meter. We know that if your point load is acting in the simply supported beam, the bending moment diagram will be in the shape of a triangle. If the UDL is acting, the bending moment diagram will be in the shape of a parabola. In most of the cases, the free moment diagram will be positive. It will be rarely negative when there is coupled moment in the beam. Now let us draw the end moment diagram. We have already calculated the final moments. Using these moments, we have to draw the end moment diagram. In the point A and in the point C, the moments are 0. So the end moment diagram will be 0 in the points A and C. In the point B, we are having two moments, MBA and MBC. MBA is acting in the clockwise direction and MBC is acting in the anti-clockwise direction. For drawing the bending moment diagram, we have to see the direction of the arrows. Both of the arrows are indicating upwards. That means we have to fix this point above this line. Then we can join this point from the point A and from the point C. We already know in the point A and in the point C, the bending moment is 0. Even though we are having two movements here, we should not make 2 points. Only one point we must make because both of these arrows are indicating upwards. End moment diagram will be negative if it comes above this line. If it goes below the line, that will be positive. Right now it comes above the line, that is why it is negative. We have made the free movement diagram and end moment diagram. Now let us combine both of them and draw the bending moment diagram. After combining, wherever they are acting alone without mingling, we have to mark them. Here we are having the free movement diagram alone, so we are marking as positive. Here end moment diagram, so negative. Here free movement diagram, so positive. Then we have to mark the values also. Wherever the free movement diagram and the end moment diagram are acting together, we are not marking anything, we just keep the space empty. If you are very experienced, no need to draw free movement diagram and end moment diagram. You can directly draw the bending moment diagram and save a lot of time. Now we are going to end this session. Thank you for watching this video.